Hello everyone, I'm Dr. Shukla. Welcome to Learning with Dr. Shukla. Rubber and clay are widely used in our daily life. For example, tires are almost always made of rubber, while clay is used to make bricks and containers. But have you ever asked yourself, do they have something in common? Surprisingly, yes. The answer lies in a simple concept from school physics. Rubber is a flexible material made of long chain molecules called polymers, mainly of carbon and hydrogen. It comes from natural latex obtained from rubber trees and is processed to become usable. Rubber can also be made artificially from petroleum-based chemicals through industrial processes. Clay, on the other hand, is a naturally occurring material made of very fine mineral particles. It can deform easily, especially when wet, because the particles can move and rearrange under pressure. When these materials are stressed or compressed, they do not change only in length, they also change sideways. This behavior is described by Poisson's ratio, an elastic constant that tells us how much a material expands or contracts laterally under loading. Mathematically, we define Poisson's ratio mu as the negative ratio of lateral strain to longitudinal strain, where lateral strain is the change in lateral dimension divided by the corresponding initial dimension, and longitudinal strain is the change in length divided by the original length. In simple terms, it quantifies how much a material deforms sideways relative to its deformation in the longitudinal direction. Now, here is the key point. For most conventional materials, including steel, aluminum, concrete, and many drained soils, Poisson's ratio typically ranges from about 0.1 to 0.3, although the theoretical range for isotropic elastic materials is from -1 to 0.5. In practice, some materials such as geosynthetics may show values greater than 0.5, and in special cases it can even be negative, as seen in auxetic materials such as engineered foams that expand sideways when stressed. For a linearly elastic material, mu is equal to 0.5. Rubber is a good example of such a material. Similarly, saturated clays under undrained loading conditions also exhibit mu approximately equal to 0.5. So, what does this really mean? Let us explore. Volumetric strain epsilon V is defined as the ratio of change in volume to the initial volume of a material. It is equal to the sum of linear strains in three mutually perpendicular directions x, y, and z. For the case shown under a uniaxial load Q, the z direction represents the longitudinal axis, while the x and y directions represent the lateral axis. Mathematically, epsilon v is equal to epsilon L plus 2 times epsilon lat. Using Poisson's ratio, you can find epsilon lat is equal to minus mu times epsilon L. Substituting the volumetric strain, epsilon V is equal to epsilon L times 1 minus 2 mu. For mu is equal to 0.5, the volumetric strain becomes 0, as you see the calculated value. This means there is no change in volume during loading. Hence, when such materials are compressed, they expand sideways significantly, but their volume remains almost the same. In engineering terms, we call such materials incompressible. Rubber behaves this way because of its internal molecular structure. Saturated clay behaves similarly because the water within the pores cannot escape quickly, especially under undrained loading. So, even though these materials are very different in origin, they exhibit similar volume behavior. And this is very important in civil engineering. Engineers use this concept when analyzing undrained conditions, short-term loading of soils, and foundation or stability problems. Before I conclude, let me leave you with a question. What other similarities can you observe in the behavior of rubber and clay? Think carefully and do share your thoughts. Now, let us reflect on this. Sometimes people may look very different on the outside, just like rubber and clay. But when pressure comes, their response can be surprisingly similar. In life, what matters is not only how we look or where we come from, but how we behave under any kind of pressure. If we observe carefully, we can understand others better and also understand ourselves better. Observe, think, and learn. If you found this episode useful, please subscribe and share it with everyone. See you in the next episode.